Now we are going to discuss about the sp hybridization, and we are discussing the quantum mechanics of polyatomic bonding. So now we are going to see what is happening to the bonding in this type of polyatomic molecules. For more clarity and precise discussion, we are going to take the beryllium hydride as an example, where you can see the beryllium is bonded to two hydrogen atoms. And as you know, the beryllium, which is having 4 electrons, 2 of it is in the 1s orbital and 2 of the electrons is in the 2s orbital. This is for a ground state case, but when we are considering the excited state, you can see that the 2 electrons is in the 1s orbital, where we will say it is the core orbital, where the electrons are not so much sort of closed or highly interacted with the nucleus of beryllium, and the other 2 electrons, one is in the 2s orbital, and the possibility of the electron is being excited to the 2p type of orbitals. And in this case, we have to say that the electron is in the pz orbital, that we will discuss later. And next is the hydrogen atom, where the electron is being in the 1s orbital. Now you can see that the valence orbital in both the cases are 2s and 2p in the case of beryllium, and in the case of hydrogen, that is the 1s orbital. So beryllium hydride, being a linear molecule or a molecule with a linear geometry, we know that it is having a bond angle of 180 degree. So coming from a diatomic to a polyatomic molecule, we are going to discuss how the valence orbital of these atoms are participating in bonds to generate a corrected kind of orbitals for optimal bonding. It means how the orbitals are being oriented to promote a hybrid type of or a less energy or an optimal bonding with high stability. We are going to discuss about that, how it will help to attain a better covalent bonding with a better orientation. As already discussed that beryllium is with the 4 electrons and hydrogen is with the 1 electron. And in the excited state, you can see that the electron is in the 2s and 2pz orbital, which are the valence type of orbitals in the case of beryllium hydride. In the case of beryllium, you can see that the 2px and 2py, they must be orthogonal to the molecular axis. For better understanding, you can see the diagrammatic representation given below. That is, here you can see 2 hydrogen atoms, and centrally this is the beryllium atom. You can see the 1s and 2s. Probably it is the 2s orbital. You can see the center, and center is the nucleus, and the 3 different types of p orbitals. That is, one is pz, the other is px, and the other is py. So that for better understanding, you can see that I have denoted the axis along this bond as z, and along this direction is x, and this is the y axis. So probably the pz orbital is along this way, and px is along this way, py is this way, and pz is along the covalent bonding axis type. So you can see that this is the case of hydrogen. This is 1s orbital, and this is the other hydrogen atom on the right side. That is also the 1s orbital. So you can see that the probability of bonding is done with the help of this pz orbital, because pz is the valence shell, you can see. Also the C is also participating because there is a mixing of orbitals is happening. There is S and P type of orbital mixing is happening there. So the valence orbital is probably the S and P. Therefore, we can say that in the case of the basic concept of, with the help of the basic concept of valence bond theory, we can say that these are the bonding orbitals found in the case of a beryllium hydride. That means 2s and 2pz for beryllium, and in the case of hydrogen, that is 1s. We can call this as the bonding orbitals. We can call this as the bonding orbitals. And we are looking at the linear combination of this 2s and 2pz orbitals of beryllium to form the hybrid orbital. And in this case, you can see that the 2px and 2py both are orthogonal to the molecular axis, and also they are also orthogonal to the hydrogen atom also. So for in the case of 2px and 2py, the net overlapping is 0. Similarly, in the case of the 2pz, there will be maximum overlapping is possible in the along 2pz, so that the covalent bonding is formed along that direction. And now we are going to the next case. And also one more thing, that is we have to say that the 2px and 2py, that we will call as the non-bonding orbitals, where the probability of bonding is very less, or the overlapping is very low. So these bonding orbitals, that means the above orbitals we have discussed before, that is 2s and 2p of beryllium and the 1s of hydrogen. So these bonding orbitals are such that they are optimally aligned to be oriented for good overlap to form a good bonding. Then only we are able to say that a good covalent bonding is obtained. Good covalent bonding is obtained. So we are now going to propose the wave function for that. That is, surely wave function, total wave function psi can be obtained by the linear combination. Surely it is a linear combination of the bonding orbitals. So we have discussed about the four bonding orbitals, and the others are the non-bonding orbitals, where there is less probability of overlapping, and we are considering only the combination of these bonding orbitals, the discussed four types of orbitals. Now we can write like this. There is psi, that is actually total wave function psi is equal to C1. This is actually the linear combination. That is C1 psi 2s corresponding to beryllium plus C2 psi 2px z of beryllium plus C3 into psi 1s of hydrogen 1, first hydrogen atom on the left side, and the fourth one C4 psi 1s H2, that is the hydrogen atom of the second case. So that is the hydrogen on the right side, that we can see that is a linear molecule. Now what is the hybridization of these polyatomic molecule? So we are going to write like this. That is the psi sp, that will be equal to 1 by root 2 into 2s beryllium plus or minus 2pz beryllium, where 1 by root 2 is the normalization constant. So psi sp, that I have written is actually the orbital of the central beryllium atom, which are orthogonal to each other. That means this is the equation for two orbitals which are hybridized. That is, one is surely 1 by root 2 2s plus 2pz, and the other orbital is the 1 by root 2 2s minus 2pz. Therefore these two hybrid orbitals are participating in the covalent bonding. I think you got the idea, because these are the total wave function of the system. Even though we are considering the total wave function, we must understand the orientation, that which hybrid orbitals are participating in the covalent bonding. As the central atom beryllium, we are taking the two orbitals This is the two orbitals, wave function for two orbitals. That is 1 by root 2, 2s plus 2pz. And the other wave function is the 1 by root 2, 2s minus 2pz. And we are going to look how these two wave functions are participating in the SP hybridization. Now, one peculiarity is that both these wave functions or both these orbitals are orthogonal to each other. And how we are going to look at how they are making the bonding. Now we are going to look at how they are making bonding. You can see this is the mixing of S and P orbitals, and this is how it looks like. For positive or constructive type, in this case, first case, you can see that this is the result. You can see this is the result where the positive S orbital is mixed with the positive side of the P orbital. So that there's a bulging is occurring on the left side. This is a constructive type of bond mixing, and this overlapping of orbital, and this is the final result of this hybridization. It's constructive one, and negative, this is the attractive one. This is how this mixing will result like this, just opposite of the first one. But though the overlapping is here, this is the overlapping is constructive, and here it is the destructive type of overlapping is happening, and two types of orbitals which are orthogonal to each other is resulting. These are the two possible orbital mixing SP hybridization mixing resultant orbitals will look like this two. This is the resultant SP after hybridization or mixing. And the main peculiarity is that both are orthogonal to each other. And these two orbitals, these two mixed orbitals are optimally oriented to form a bond. That means the covalent bond, which with one of the hydrogen atom. That means this this hybrid orbital is mixing with one of the hydrogen atom, and the other orbital is mixing with the other hydrogen atom. So as a result of this overlapping, we are getting the beryllium hydride bonding. That means one hydrogen atom is mixed with one of this hybrid orbital, and the other hydrogen atom, one orbital is mixed with one of this orbital. This is the resultant of the mixing, constructive and destructive type of mixing. This is the result. Now we can say that these two orbitals are optimally oriented. In order for that, we are getting a very good covalent bond between two hydrogen atom. This is how the chemical bond looks like. So now we are looking accurately how constructive type of bonding is happening. Now you can see that this is the hybridized or hybrid orbital that is being mixed with the 1s orbital of hydrogen atom. This is combinative or constructive type of mixing or overlapping, which result in the sigma bonding. That you can see that after mixing, you are getting a completely overlapped type of orbital. This is how it looks like. And the second case, the hybrid orbital is mixing with the 1s orbital of the oppositely hydrogen atom. And finally, you are getting a orbital like this. This is the sp type of hybridization. And this is considered as the bonding orbital, which result in this type of overlapping, which will result in the bonding of orbitals. And also there are two other possibilities are there, that is anti-bonding or destructive type of bonding, where you can say that there is ineffectively there will be no bonding. The overlapping is is not up to the mark, or you can say that it is not the correct oriented way, so that this will not result in the bonding. So we are saying that it is an anti-bonding type of orientation. Here also two possibilities there. This is a hybrid orbital, but still you can see that this is different from the first one. This is the opposite one, where the polarity is reversed. The polarity is different, is opposite, reversed. You can see the difference. You can see that This is just opposite to this one. The polarity is just opposite to each other. You can see that this type of orientation is not up to the mark, and it will result in a bad overlapping and the formation of a knot. Here, and this will not result in a covalent bond. And similarly, in the second case also, with the second hydrogen atom, can say the orientation or the overlap is not very good, or is not up to the mark, and finally resulting in the formation of a knot. These are the two antibonding type of orientation, or this two types of orientation will not result in the case of bonding, covalent bonding, but the formerly two types will result in the effective covalent bonding. This is what the quantum mechanical treatment of sp hybridization looks like. Thank you.